Hi there. We're going to talk about section 3-4, inverse functions and relations. Let's give a definition first. Let's talk about what an inverse relation is. Okay? And here's the way this definition is. Two relations, let's call them F and G, are inverses if and only if. Remember, IFF is the proofwriting notation for if and only if, for a point, let's call it A, B, where A is the X and B is the Y. For a point A, B in F, there is a corresponding point in G that is BA. So in other words, we switch the X and Y coordinates. Okay? So that's what inverse relations and inverse functions do. They switch the X and Y coordinates. Okay? A notation note is that the inverse of some relation or function F is written as F inverse, like that. You don't need the quotations. I'm just using that to help you see what I mean to write. Okay? One other thing, and I guess I'm going to do it on a new board, is that two functions, let's call them f of x and g of x, two functions are inverses if and only if the composition in both directions is the same, and not only is the same, but the composition in either direction equals x. Okay, and that's a good way to verify that two functions are inverses. You can prove it really easily with that. Okay, so one of the things that this allows you to do is to graph inverses without even knowing their equation. Okay, so let's start a new board here, and let's do our first example. Example 1. Let's graph this function, f of x equals negative 1/2 times the absolute value of x plus 3 and its inverse, F inverse using tables. Okay? And the tables thing is going to be really important and helpful to us. So let's do a table for f of x. That is that equation right there. Okay? And I'm just going to pick some numbers. Typically, if you don't know what it looks like or don't know how helpful things are going to be, it's pretty good to pick -2 through 2, those 5 values, and then you plug them all in and get answers, and usually that's pretty helpful. So what happens if I plug in -2 for x? Well, I do the absolute value of -2 is +2, and -1/2 times +2 is -1. -1 plus 3 is 2. What happens when I plug in -1 for x? Well, the absolute value of -1 is +1. -1/2 times +1 is -1/2. -1/2 plus 3 is 2.5. And I'm just going to write it that way. I could write it as 5/2 also, but it's pretty easy to come up with 2.5 there, and that's pretty easy to find on a graph, so I'm going to leave it that way. For 0 is always an easy one. Plug in 0 for x, and you get the absolute value of 0 is 0. 0 times -1/2 is still 0. 0 plus 3 is 3. So there's that one. When I plug in 1 for x, that's the absolute value of 1, which is still 1. The absolute value of anything is the positive value of that thing, so the absolute value of 1 is 1. -1/2 times 1 is -1/2. -1/2 plus 3 is 2.5. Then I'll plug in 2, and the absolute value of 2 is 2. -1/2 times 2 is -1. -1 plus 3 is 2. Watch how easy it is to get the table for the inverse. Okay? One of our definitions for the inverse was that it is switching x and y. These are the y's. So I'm just going to write them in the x's. And then here's the x's from f of x, and I'm just going to write them in the f inverses, that is, in the y column, in the same order. And voila, I have a table for the inverse without even having to know what it is. Okay? So I can graph both of these. Let me do them in 2 different colors. I'll do f of x in blue. Okay? So let me make my marks in black so that they're the same everywhere. And let's go back to blue, and we'll worry about f of x first. And f of x has points of -2, 2, so right there, -1 and 2.5, so up there somewhere, 0, 3, 1 and 2.5 and 2, 2. So it looks kind of like that. Oops. And kind of like that. So there's our f of x. And in red, let's do our f inverse. So f inverse is 2, negative 2, 2.5 and negative 1, 3, 0, 2.5 and 1, 2, 2. And this one looks like that, kind of like that. I messed that up a little bit, but that's okay. So there it is, and notice that they both, and I'll do this in black here, notice that they both have a common point at 2, 2. Turns out that that's really important because, let me show you in purple here. If you draw this line right here, this is the function f of x equals x, equals x. And if you notice, the two graphs are mirror images of each other over that line. They are reflections of each other over that line, and that is true of all inverses. All inverses are reflections over the line y equals x, the line f of x equals x. So let's switch colors. Let's go back to black, and let's talk about something new. Let me start a new board here. But let's talk about how you would decide whether a function has an inverse that is a function, okay? So we're going to use the horizontal line test to decide if an inverse will be a function. And the way this works is you have to remember that there was the vertical line test. And the vertical line test helps you decide whether things are functions. The horizontal line test helps you decide whether the inverse of something is a function or is going to be a function. Okay? So let's talk about example 2 here, and I think this will become a little bit clearer. Let's suppose we're talking about a function f of x equals, let's say, x plus 3 all squared minus 5. Okay? And what I want to know is f inverse a function? That's the first thing I want to know. And we'll figure out the rest as we go. So let's answer this first. And the way I'm going to answer this is by sketching this, okay? And I'm going to sketch this by noting that part there and that part there give me shifts. So I've got here, that is a shift in the x direction of -3. That's told by that. It's -3 because it's grouped in with the x, and things that are grouped in with the x happen in the x direction happen opposite of what you expect them to. And then I've got a shift in the y direction of -5. That's coming from there. And things that happen not grouped with x tell you about what's happening in the y direction, and they happen as you expect them to happen. So what happens is I keep in mind the parent function, which is a basic parabola, because this is a second-degree polynomial. It's a parabola. It's quadratic. Lots of different names for this because it's relatively important. I shift the x part of it by -3. I shift the y part of it by -5. That puts my vertex right there. And then other than that, it looks like a parabola. Now, let me switch colors here. And let's talk about the inverse. Notice that if I take a horizontal line and run it somewhere, and you only have to have this happen once, but if you take a vertical, or not a vertical, a horizontal line, and run it anywhere, put it anywhere on that function, if it touches two spots on the function at the same time, then you fail the horizontal line test. So what we're going to say here is F inverse is not a function and the reason is because it fails the horizontal line test. Okay, so that's the first thing I want to do with that. Let me start a new board, and let's talk about another thing to discuss with this. And the second one is to find F inverse. That is to find the equation for F inverse. And the way we're going to do that is we're going to go back to the rule of exchanging x's and y's. Okay? So I'm going to write that original function as y equals instead of f of x equals. So it was f of x equals, so now it's going to be y equals x plus 3 all raised to the second power minus 5. So that's step one. Step two is to exchange x and y. Every x becomes a y, every y becomes an x, and solve it again for y. Okay? And the way that's going to work is, I'm going to write it this way. X equals, and then I'm going to put y plus 3 all squared minus 5. And what we're going to see is that if I solve it for y, some things are going to happen. So let me start solving it for y. I'm going to add 5 to both sides. I'll get rid of that minus 5 or that negative 5 if you want to think of it that way, giving me x plus 5 equals y plus 3 all squared. Now I need to get rid of that squared. I'm going to take the square root to do that. Square roots cancel squares. It is the inverse operation of it. And here I have to do plus or minus the square root of all of that. The reason that I have to do plus or minus is because I have to account for the fact that if I tell you I squared a number and I got 25, I could have squared 5, or I could have squared negative 5. And you have no idea of knowing which one I started with because I haven't told you. So you just account for both cases, and that covers you in both situations. Okay? So then you wind up with plus or minus the square root of x plus 5 equals y plus 3. So this plus or minus creates two different things. This is just the notation to keep it all wrapped up into something that looks like one equation, but really isn't. And then I have to do this minus 3, and typically we put it as a negative 3 out there, so we wind up with negative 3 plus or minus the square root of x plus 5 equals y. And that is the equation for F inverse. So that takes us through how you get F inverse. Okay? One last thing that we could do, and I'm not going to really go through it, but another thing that we could talk about is how to graph each one. I could graph the function and its inverse. The function is real easy to graph. We did it before. Let me graph it. Well, let me make some marks here first. Again, I could build tables and invert those tables, make every x a y, every y an x. But there's another way. So let me do the f of x in blue. And remember, there was a shift of negative 3 in the x direction. So I'm going to shift over by negative 3 in the x direction, and a shift of negative 5 in the y direction. So 1, 2, 3, 4, 5. I'm going to go left 3 and down 5, and that's going to be the new vertex for this parabola. And so there's the original function. Okay? Let me do the inverse in red. So the original function is in blue. I didn't switch it. The new function, not function, again, not a function. The new relation, the inverse relation, is going to be in red. And the way I'm going to do that is I am going to draw the line y equals x, which looks like that. And since inverses are always mirror images, that is reflections, over the line y equals x, I know, first of all, that that has to be a point, that has to be a point, and its vertex has to be the inverse of the vertex that I had. So the vertex that I had was negative 3, negative 5. So it's got to be negative 5, 1, 2, 3, 4, 5, and negative 3, 1, 2, 3, which is pretty close to right there again. And I know it's got to look something like that. And it should be a little more symmetric right there. I didn't make that quite as symmetric as I'd like it to be, but we're sketching here, so. But you should see the reflection there. It should be pretty obvious, okay? So that is doing a lot of different things with inverses. I'm going to talk about verifying them next. Okay, so let's back to black. Yes, let's say we have a function f of x, and let's say f of x equals something sort of simple here, 4x minus 9. Let's do a couple things. Let's find f inverse of x, because it turns out that the inverse is a function. And we will verify that f of x and f inverse of x are inverses by composition. So those are the two things that we'll do. On this board, I'll find f inverse of x, and on the other board, I'll do the verifying. So let's write f of x equals 4x minus 9 as y equals 4x minus 9. And I will, in the next step, I will exchange x and y, and I'll solve. So let's add 9 to both sides, and we'll have x plus 9 equals 4y. I'll divide by 4, and that means I got to divide this whole side by 4, giving me y equals x plus 9 all over 4, so that's my f inverse of x. And I know this is a function, by the way. I know now that it's a function without having to graph it because I got one answer. In the previous problem, notice that when I solved, I got two answers, a negative 3 plus stuff and a negative 3 minus stuff. And that is that is another way of knowing that it's not a function, because when I solve it for y, I get two answers. If it's a function, when you solve it for y, you're only going to get one answer. So let's do the second part of this. Let's verify by composition. Okay? Let's do that on another board. So I've got f of x equals 4x minus 9. I've got f inverse of x equals, what was that? X plus 9 all over 4. And so what I'm going to do is I am going to take the composition, and let's do it that way. Now, that open circle means composition, and typically we read them backwards. So this actually reads f inverse of, f inverse composite f of x. So I'm going to do f inverse composite f of x, which means f of f inverse of x, which means that if I go to f, so over here is the f, and I put parentheses around every instance of x, and I replace those parentheses with what f inverse of x is. So if I replace it with x plus 9 over 4, and then simplify the whole thing, I'll get something. Okay? So I'm going to do that. In this right here, that x is going to turn into x plus 9 all over 4. Replace parentheses with parentheses. So now I've got 4 parentheses, that 4, by the way, parentheses, and then I've got this parentheses x, but instead it's going to be these parentheses, so x plus 9 all over 4, and then minus 9, that minus 9. Notice there are no parentheses there, so that's why I'm not doing anything extra with it. So now I've got a 4, and that 4 is actually on the top of this fraction. That is, it is being multiplied by that fraction And when you multiply fractions by things that are not fractions, you are multiplying them on the top. So I've really got 4 divided by 4, which is 1. So those cancel. And I'm left with x plus 9 minus 9. Well, 9 minus 9, that's 0. So that's x plus 0, which is x. And so now I've shown, and really we should do it in both directions, but I'm just going to show it in this one direction, and you can verify the other direction for yourself. I hope this has helped. Thank you.